the last lecture, we have come across the important parts of corrosion. First is there must be cathodic reaction. There must be cathodic reaction, that means electron accepting reaction or reduction reaction. Now, there should be anodic reaction to supply the electrons are required for cathodic reaction or reduction reaction. This is oxidation reaction. Now, we have already seen that if you take this part and this part, then you must have redox reaction in case of corrosion. Now, third thing is there should be electrodes, and cathodic reaction occurs on cathode, and the sign of that electrode might change in case of a cell where you get electrical energy from chemical energy, or the most common example is a galvanic cell. There the cathode is positive terminal, or the cathodic reaction occurs on positive terminal. But let us say in case of electrolytic cell where you supply electrical energy and get chemical reaction, in that case cathode is the negative terminal, or in the negative terminal you have cathodic reaction. So, you have cathode, consecutively you have anode where anodic reaction occurs or oxidation reaction occurs. Now, all these things, there must be one more thing, that is there should be electrolyte. There should be electrolyte which carries the charge in the solution. So, these are the components. And now, in case of aqueous corrosion, let us say zinc corrosion in HCl, we have seen that these things are there in case of a corrosion cell. Now, in the same way we have taken the analogy of that corrosion cell and compared in case of dry corrosion or oxidation. In the oxidation also we have seen that if you have a metal and then metal oxide and then gas environment, you have two interfaces, then one interface will act as anode where anodic reaction occurs, or in this interface where you have metal ion formation from metal, that means 2E metal, that means here anodic reaction occurs, this interface is anode, and in this interface would be cathode, because oxygen will combine 2 electron, will go to oxygen 2 minus, this is cathodic reaction, this occurs here, and this electron transition takes place from this end to this end. The migration of electron takes place through this metal oxide layer. So, this electron is going and this electron is taken by oxygen, and then this reduction reaction is taking place. Now, depending on whether oxygen ion will come here from this surface to this surface and combine with metal oxide and then form MO, which is M plus 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 O minus. So, this reaction can take place here, or this reaction can take place here where metal ion will go from this end to this end via this metal oxide. Here metal oxide acts as electrolyte. So, now you have the same analogy here, you have cathodic reaction, you have anodic reaction, you have electron transition, electron migration through the metal oxide layer, as well as ion transition, ion migration from through the metal oxide layer, either from this end to this end or this end to this end. So, metal oxide is acting as electrolyte. So, this is also a sort of corrosion cell. Now, let us get into the basic thermodynamics of these corrosion cell. when you talk about thermodynamics in case of corrosion, then before that we should understand G. This G is known as Gibbs free energy. Gibbs free energy. See, this Gibbs free energy, from this we can get the idea of a spontaneous reaction or an equilibrium or a non-spontaneous reaction. Now, G is considered to be the energy of energy, that is, this G is absolute G is very difficult, it is not possible to determine, rather we always determine del G, which is the free energy change, and this free energy change is nothing but the energy which is available for doing work. Okay. So, now this free energy, when it goes to 0, we call it as equilibrium. We call it as equilibrium. The system has reached equilibrium. Now, if this free energy is less than 0, we call it spontaneous reaction. Now, if it is greater than 0, then it is non-spontaneous reaction. Non-spontaneous reaction. Now, here we are missing something. The missing part is a system always is to be defined with respect to some parameters. Okay. Until unless we define that parameter, the system cannot be thought of properly. Here, whenever you consider this, you must mention that there should be two other parameters which define the system, that is pressure and temperature, those are constant. So, when del G Pt, that means that at constant pressure and constant time it goes to 0, that time it goes to equilibrium. And here also you have to mention Pt, which is basically nothing but at constant temperature and pressure. Now, this is the three conditions to determine whether the system has reached equilibrium, or the system is spontaneous, or the system is non-spontaneous reaction. In the system, non-spontaneous reaction is taking place. Now, this, let us say, now with this idea we will go into the equilibrium constant. Now, let us say we have some reaction A plus B is having equilibrium, which is the equilibrium sign, C plus D. This A, capital A, B, C, D are the components, or this case, let us say this side is reactant. Initially I have started with A and B, capital A and B, these are the two components of the system. Then when reaction happens, then it forms C and D, capital C and D, these two products. Now, while doing that, then you have A mole of capital A and small b mole of capital B, they are reacting and forming small c mole of capital C and small d mole of capital D, these are the product phase. Now, when you have this thing, then you can relate this rate of this reaction by this simple expression, which is rate, let us say rate of the forward reaction. That means, if we consider this is to be forward reaction and this is to be reverse reaction, reverse or backward reaction. That means, when you have initially you had only A and B, reaction has started, now it forms C and D, but when it forms C and D, then if you have the active masses of C and D, then the backward reaction also will start. But initially the rate at which the forward reaction occurs would be higher than the rate at which reverse reaction occurs, because the active masses which are participating in the reactions would be different for the product phase as well as for the reactant phase. Now, that case, the rate at which the forward reaction is taking place, that can be related as a simple expression which is called K1 C of A, the concentration of A. This C is the concentration, rather since this is, we are considering a C here, let us put it in this term, which is, let us have a term like C dash, because just to have the difference between the C component and the concentration. Now this C dash A, now it should have, because we have A mole of A, so there should be concentration of A to the power A, small a, into concentration of B to the power B. This is my forward reaction, or the concentration with respect to concentration, the rate at which the reaction occurs can be expressed in this way. The same way, the reverse reaction, which is given by the reverse arrow, can be written as K1 C dashed C capital C into C D capital D, and in this case it should be 2. This K1 and K2, those are rate constants, and these are having, now if you consider the rate at which forward reaction occurs and the rate at which reverse direction occurs, initially the rate, if you consider the rate, let us say rate, and if you consider time, now initially the rate at which forward direction occurs would be at a much faster rate, because the active concentration would be much higher, because initially you have started 0 concentration of this and you have the maximum concentration of this. Now as it forms, gradually your active masses is going down, so the rate of the forward reaction will go down like this. Now once you start forming this, because of this reaction, now you have that active masses to start initiate the reverse direction reaction. So now initially you had almost let us say you had this almost 0 reaction rate, now you have started a reaction for the backward direction. This is forward, this is backward. Now after some time, this rate at which forward reaction occurs and the rate at which reverse direction reaction occurs, then those two rate would become equal. So when this rate becomes equal, these two rates it becomes equal, then we call it as that the system has reached dynamic equilibrium. Now when the system has reached dynamic equilibrium, that means rate forward equal to rate backward, both are same. If these are same, then I can write that K1 by K2 can be written as C dash C dash D by C dash A C dash B. Now this ratio K1 by K2 equal to C dash into C D this is termed as Kc, which is called as nothing but constant if T remains constant. Fine. Now if you have this thing, and this is called equilibrium constant. Equilibrium constant for this reaction, for this equilibrium. Now if Kc, this K is termed as Ka, then it is called as, then the species are considered not in terms of mole fraction, it considered as activity. Okay. Now instead of C, if you replace it by A, then it is called as, this thing will change from C to A, which is the again equilibrium constant, but the active masses are considered in terms of activity, and activity and concentration is related in according to this formula, activity with this formula it is related. And here C is molarity, and F is fugacity or the activity coefficient, and this F becomes 1 when system is a very dilute solution, or the system when the system is ideal solution, or the solution if the system is ideal. Okay, that case A would be equal to the molarity. Now this formation of Ka or the Kc with the active masses or the concentration, that thing was found out by two famous scientists. Those scientists' names were Norwegian chemist Gullberg and Vage, and they called it as laws of mass action. This they found it in 1867, and it says that at a constant temperature the rate of a reaction, chemical reaction, is proportional to the active masses of the reacting substances. So that means in the forward side these are the reacting substances, if you consider the backward reaction these are the active reacting substances. So now according to that we get Ka or Kc. Now how would we relate this one, the equilibrium constant, with del G? Let us see that, or the free energy, how the free energy is related to the equilibrium constant. When a system is an open system, that time the free energy of the system is a function of pressure, temperature, and if you have n number of components in the system, then each individual species will have some effect on the free energy of the system. So it is also related to, let us say, N1, N2, N3 and 1, 2, 3 up to Nn. These are the components, 1 to n are the components, and n is the number of moles of those components in the system. Now if you have this, then if you have a small change in the system, let us say small change is taking place of in each of those parameters, let us say P, T, N1, N2, N3, those mole fractions, they are changing, and what would be the change in G, that can be expressed as plus so now you have small changes in P, then what would be the change of that pressure towards that free energy of the system, that is given by this. Now if you have a small change in T, the temperature, then what would be the change of that T towards that free energy of the system, that is given by this, provided the other terms are constant. Now in this way you can also express, the full expression, you can have the full expression for changes in individual species towards the free energy change of the system. So then again del G N1 P T N2, because N1 we have seeing the change in the N1, and then what would be the change towards the free energy, then other things are kept constant. Like that you can have all those expression. Finally you can have del G D N N of nth species P T N1 N2, like that up to n minus 1, because you have taken nth species and there are n number of components. So then you have to end with n minus 1 into dn n. Now, these are all the contributions towards the free energy change. Now, if your system temperature and pressure, those are constant, then this as well as this both are becoming 0. Then the overall change of the system would be decided by the change in the other components. That means N1, N2, N3, N4 like that up to the nth species. Now, this is basically the physical significance of this is the rate of change in G if you have 1 mole of addition of one first component into the system if the other components are same or constant. Now, this is also called as partial molar quantity, and this is also called as chemical potential. And this chemical potential is termed as mu. Now, if you have this, then you can express by taking this part as mu1, because you are seeing the change in first component, and then you are seeing the what would be the effect on free energy change of the system. So, this is considered as mu1. Then this is the change in one species, the first species of the change in mole in case of first component, like that you can express it as dN2 plus mu3 N3, like that it would move, then mu n dN n. So, now I have the final expression like this. Now, let us say you have a system, you have n number of components, pressure and temperature constant. Okay. If you have n number of components, pressure and temperature both are constant, in that case let us say I have a small fraction of change in each component. Let us say that small fraction of change is del x, or del x fraction mole is changing in every component. If you have this fraction, this is fraction, and this fraction is having this change dx is going to happen in all the components. Now, what would be dN1? dN1 would be, if there is N1 number of moles for first component, then dN1 would be the small change in the system, that is the fraction, into the total number of mole for first species. So, first component. So, N1 into del x. Same way dN2 would be N2 del x. Like that it would move. So, dNn would be equal to Nn del x, and del x is the small fraction of change in each component. If you have this, so in the system initially the free energy was G, and if you have the same fraction of change, then what would be the del G? Del G would be absolute free energy into the change, fraction change would be equal to del G. So, if you replace it, then it would be equal to G del x equal to mu1 del x N1 del x plus mu2 N2 del x, because we have already seen dN1 is equal to N1 del x. Like that it would move. Finally, it would have mu n Nn del x. So, what would be my final expression? Final expression would be G is equal to mu 1 N 1, because these terms are getting cancelled. So, mu 1 plus mu 2 N 2, like that it would move. Finally, you will get mu N N N. Now, this is one of the expression for Gibbs-Duhem relations. There are three Gibbs-Duhem relations. The first one is nothing but the first relation for Gibbs-Duhem. There are three. This is first Gibbs-Duhem relation. This is second Gibbs-Duhem relation. Now, you can also get the third one if you just differentiate this term, other terms, and then replace this thing into this after differentiation. For example, if you differentiate this, then you will get mu 1 dun 1 plus mu dn 2 dn 1 d mu 1, like this expression you would get, and replace this, and finally you would get that this term and this term are same. So, you will get this term everywhere. If you differentiate the each term there, you will get two terms. One of the term will be same as this first expression. Now, then you replace it, you will get it will all get cancelled, and you will be left with these terms only, and this would be equal to 0. That is another Gibbs-Duhem relation, but we will stick to this part, because this part will give you some idea. Then finally you will come to have some relation with del G and equilibrium constant. This is my relation. Now, let us come back to the same reaction. If you consider the same reaction, let us say this reaction is happening in the forward reaction. And let us say I consider in terms of activity. So, activity of A is A, activity of B is B, activity of C is C, and activity of D is D. Now, let us say I go from this end to this end. The free energy change for this system would be, free energy change for the system would be G of product minus G of reactant. G of product and G of reactant, if you have this, that means the final, whenever you consider some free energy change or the change in the state function, then let us say one state to another state, this is first step, this is second step. Now, if you have this change, then your change in the function would be, here it is del G, then change in the function would be, it is G2, if it is G1, so G2 minus G1. Now, if you have some free energy associated with this reactants, you have some free energy associated with this product term. Now, if you go from this end to this end, now you are having some change, that means you are going from G1 to G2. And what would be my free energy change? Then G2 minus G1 would be my free energy change. And so, for this process, this is my free energy change. Now we know this relation we know, and this relation is valid, let us say for a particular system. Initially we have the reactant. So, let us consider only the reactant part. The reactant part, if you consider, so what would be my free energy for the reactant, or the G1 in this case would be equal to mu 1 or mu A, because you have considered two components, A, capital A and capital B. So, mu A into, you have to see the number of moles there, number of moles is A plus mu B. What is my reactant? this is my reactant case. Let us say I would like to consider the free energy for this system. Now, in that case it is basically nothing but product, or in this case this is G2 is nothing but small p c, which is the number of mole of C component. So, mu C plus d mu d. Now, mu is also, this chemical potential is also expressed as mu 0 plus RT ln activity. Let us say you are considering the activity more, if you would like to find out what would be my chemical potential of A, then chemical potential of A would be basically nothing but this is nothing but the standard state chemical potential for A, and this is activity of A. If you find that this is the relation, then you put it here. You have to just replace this thing. Instead of mu A you put this, instead of B you just change this sign, capital B. The A would be replaced by capital D. Similar way it would be all capital C, capital D for mu C and mu D. Now, if you put all those things, then you would get this expression. Let us say A mu A 0 plus A RT ln activity of A plus mu B 0 plus B RT ln A B. Similar way, this can be written as C mu C 0 plus C RT ln A C plus D mu D 0 plus D RT ln A D. Now, what would be my free energy change for the system? Free energy change is this minus this. So, if you consider this is as G1, this is as G2. So, del G basically nothing but G1, G2 minus G1. And if you do the simplification, then you would get mu C plus D mu D 0 minus A mu A 0 minus B mu B 0 plus RT ln, you just take this term to the power of this. Okay. So, now AC to the power C, AD to the power D by A to the power A B to the power B. So, you are getting this expression. Now, del G equal to, what is this? This part, all are standard values. So, if these are standard values, then it must be constant. So, this is a constant Z plus RT ln ACC ADD AAA ABB. So, this is one important relation.